Now let's take this intuition and move on into another setting where we might have some intuition, and in a commonplace setting which could well be the setting for a parlor game. Okay. Here is the question. Suppose you have an assemblage of 23 people. What are the chances that at least 2 of them share a common birthday? Pause the lecture, think about it, and see if you have an instinctive answer. At this time, do not do an analysis. We'll come to that in a moment. But what do your instincts tell you? What is your estimate? Do you think it's likely? Do you think it's unlikely? Now, if I were doing this in front of a real classroom, I could actually do the experiment, and I frequently do in class, by asking individual students, recite your birthdays, and if any of you have a coincidence, let us all know. Okay. But albeit a live audience in one physical location, let's do an analysis. Okay. So, this is a setting, and this is called the birthday paradox. We built up some intuition in combinatorial settings where we could model problems using balls and urns, and this is another problem which is rife, ready for such an approach. Let's assemble the individuals from left to right, 1, 2, 3, up till 23. Okay. Imagine they're all seated in front of you. Now, one could do this problem for 23 individuals, but it is much more satisfactory to do it for an arbitrary assemblage of individuals. So, let's imagine that we have an algebraic variable representing a fixed but unspecified number of individuals. Naturally enough, we will call such an assemblage of size n. Why n? Because, of course, it is inconceivable that I call an integer anything else. Long tradition and custom has inured us to calling integer variables n. So let us suppose that there are n individuals. And each individual has a birthday spread out through a year. And let us, for definiteness, assume that a year has got exactly 365 days. I know you'll immediately have an objection. You'll say, well, what about leap years? Now, here's where we come to the crux of modeling. Yes, in fact, every 4 years we hit a leap year. And now we have 366 days in the year, and some individuals will happen to be born, for example, on February 29th. But the idea of a leap year in a setting of this size is going to make a very small change in various chances we calculate. But it's going to add enormously to the complications we'll have to take care of. And so, as a first modeling approach, we make the default assumption that we do not have leap years, and we just start with a year with 365 days. And now we have a setting where each individual takes one of 365 values as their birthday. Naturally enough, we'll assume a random sampling from the days of the year so that each individual's birthday is equally likely to be any of the 365 days in the year. Now, this in itself is not strictly accurate. Right? If you look at human populations, especially in the temperate regions, you'll find that birthdays are more concentrated in certain parts of the year for various climatic reasons. But again, this is a second-order effect, and this only gets in the way of understanding what is going on. If for nothing else, if we assume that we have random sampling and birthdays are equally likely, we are going to get a conservative estimate for the chance of a birthday coincidence. So let's simplify further. We have n individuals. Each individual can have one of 365 days as a birthday, and we assume random sampling where every birthday is a priori assumed to have equal probability. An outcome of this experiment is a string of n digits. And this sequence of n digits represents days of the year. Each one is one of 365 days. If we think of the individuals as balls, the days of the year as urns, what we are specifying is an ordered sample of size n drawn from 365 distinguished urns. And of course, by the basic principles of counting, we know that the number of different sequences for birthdays we can get is 365 to the power n. This is sampling with replacement. Birthdays could, in principle, repeat. Out of these 365 to the power n possibilities, which possibilities result in birthday coincidences? As in the Marais dice problem, what if we consider the obverse of this event, the complement of this event, which is the event that no two birthdays coincide? If that is the case, then we are provided as an outcome a string of n digits, each one taking values between, say, 1 and 365, with the property that no two digits can be the same. But this then corresponds to an ordered sample of size n drawn from a population of size 365, the days of the year, where sampling is without replacement. And again, an elementary principle of counting tells us there are precisely 365 to the n falling possibilities for such a sequence. Remember the falling factorial notation. 365 to the n falling stands for a product of n terms starting at 365 with each succeeding term one less than the previous term. Good. And therefore the chances of not getting a coincidence in birthdays should be 365 to the n falling divided by 365 to the n, because naturally we are assuming random sampling, all days of the year being equally likely. The chance, therefore, that there is a coincidence, that two or more birthdays coincide, should be 1 minus this ratio. 1 minus 365 to the n falling divided by 365 to the n. Of course, this only depends upon the number of people in the assemblage. Let's identify that, give it a name, call it little p of n. The probability that in n individuals you find a coincidence of birthdays. Of course, this varies with n. So we could very quickly see what this behaves like by tabulating representative values. And here's what I provide for you. So let's say n runs from 5 and 10, 15, 23, and so on up. And that is in the first column. And the second column tells you what the value p of n computes to be. The row highlighted in red is the problem we started with when we had 23 individuals, and we find that for 23 individuals already, the chance of having a birthday coincidence is 50%, or actually slightly more than 50%. Many people find this very surprising. Right? And this is why it's called the birthday paradox. In fact, if you look at an assemblage of 70 people, the odds are now about 99% that there will be a coincidence of birthdays.